All right, so we're talking about the chain rule, and so the chain rule has to do with taking the derivative of a composition. And so the main thing, of course, to realize is that, or we have to be able to identify a composition when we see one. And so if we do identify a composition of f with g, then the derivative is f prime of g of x times g prime of x. Okay, so let's try a few. We'll use the examples that we had before. There's an alternative way too, right? That we talked about. So if we have f of w and w is a function of x, right, then you can compute the derivative this way. And so let's see how that works. So we'll use the examples that we had previously. 1, f of x equals the sine of x squared. Okay, and so we already know, right, that one way of writing this is that f of x is going to be x squared, and g of x is the sine of x, right? And so the notation f prime at g of x means that we're going to take 2x, right, that's the derivative, and evaluated it at sine of x, which is 2 times the sine of x. Okay, and then the chain rule says to multiply that by g prime of x, which is cosine of x. Okay, so therefore f prime of x is equal to our 2 sine of x cosine of x. Now in a similar way, you could say, instead of having all these x's up here, you could say instead that we have like f of w equals w squared, where w is equal to sine of x. And then the chain rule says that we take df over dw. df over dw is 2w, and dw over dx is just the cosine of x. Okay, and so the derivative then would be 2w times the cosine of x, but then the last step would be to replace your w, right? Here it is. Put the w back in, so you end up with 2 sine of x cosine of x again. Good. So either way you want to do it is fine. I think it's actually a good idea to learn both versions, because sometimes one version is easier to use than the other. Sorry, I just had a little allergy attack here. Let's try number 2 before I start sneezing again. H of x equals x squared plus 3x plus 1 cubed. Okay, so therefore our f of x, we said, was x cubed, and our g of x was x squared plus 3x plus 1. Okay, so therefore our f prime at g of x, right, is going to be our derivative, but then we're evaluating that at g of x. Okay, so that means that we have 3 times g of x squared. So we put our g of x in there before we write it in, and then g prime of x would be our 2x plus 3. Good, so putting these together then, h prime of x is going to be 3 times our g of x squared times 2x plus 3. Good, so that alternative way is just to think of f in terms of w, right? Oops, let's see if I can write more clearly. And w in this case was x squared plus 3x plus 1. And so therefore df over dw is 3w squared, and dw over dx is x squared, 2x plus 3. And so then h prime of x is equal to df over dw, or sorry, I guess I am writing it in terms of that. Now just fill in our numbers. And then be sure and back substitute. Good, and you see that we get the same answer either way. All right. Let's continue that. Number 3. How about h of x equals e to the x squared plus 5x? Okay, then our first way of writing the derivative might be to take f of x as our e to the x, g of x is x squared plus 5x, right? So that f prime of g of x is equal to e to the x, but then we have to evaluate that at g of x, which is e to the x squared plus 5x. And then g prime of x is 2x plus 5. So put that together, and you have x squared plus 5x times 2x plus 5. Good. And similarly, we could have written that as f of w equals e to the w, where w is x squared plus 5x. And so then we could have df over dw times dw over dx is equal to e to the w times 2x plus 5, and then go ahead and back substitute again. And so again, you see we get the same answer either way. Good. Now the nice thing, the reason I'm saying that the second version is kind of nice is because we could have done something like the following. Suppose we have f of w equals e to the w. W is a function of x, but then let's take x to be a function of t. And then we could even take t to be a function of what variable? R? Okay, and so at this point then you could see we can compute df over dw. So that's the rate of change of f with respect to w. We could compute the derivative of f with respect to x, because w is a function of x. We could compute the rate of change of f with respect to t, and that's because f is a function of w, but w is a function of x. W is, oh, wait a minute, that was right. W is a function of x, and then we could compute the rate of change of f with respect to w, and then w is a change of is a function of x, then x is a function of t. Okay, that's probably enough there. Well, we could also take df over dr if we wanted to. So df over dx would be df over dw times dw over dt, or dx first. So that'd be e to the w times 2x plus 5. And then we would want to back substitute. Here we would have df over dw times dw over dx times dx over dt. And so we would just multiply what we had before. Is that a 2x plus 5? Yes. And then we would multiply by dx over dt, which would be minus sine of t. And again, you'd want to finish by back substituting so that everything's in terms of t. And then df over dr would be the same, it would be this thing, right? Times dt over dr, which is 2r. And so you'd end up with this thing times 2r. Okay. So you can see, right, that we can take a composition within a composition within a composition within a composition, and sometimes I think it's easier to use this technique for that than it is the other. But once you get the hang of using the composition or using the chain rule, you'll be free to choose either one. I think you'll be able to use either one. Yeah, whichever, you'll get a sense for which one is easier. Okay, I'll stop there, and we might take a look at some more problems from the textbook.